Okay, so this is my NABCEP video chapter number 3. In this video, we're going to be covering the sun. Half of photovoltaics is the photo part. That means it's the sun. I got flashcards this time because my videos were apparently poorly organized. So the first thing we're going to go over is some terminology. Then I'll show you how to do a couple of formulas. We will go over the Earth's orbit and the solstices. We'll go over the elliptical and equatorial planes. We'll go about measuring the sun's position in the sky, the solar window, and tilt angles of modules. All right, first thing we're going to do is go over some definitions. I wrote them here. Edit that out later. Okay. An astronomical unit. Astronomical unit is 93 million miles or 150 million kilometers. It is the average distance between the sun and the Earth. Solar irradiance. Solar irradiance is a measure of radiation. Its measurement is in watts per meter squared. Radiation over area, or power over area. Irradiation, different from irradiance. Irradiation is the radiation over time, or the irradiance over time, usually measured in kilowatt hours per meter squared. Insolation is an irradiation that's measured over exactly 1 day. Insolation is kilowatt hours per day. Just quick recap. Irradiance is watts per meter squared, instantaneous measurement. Irradiation is the irradiance over time, and insolation is the irradiance over 1 day. Okay. Extraterrestrial solar radiation. Okay, sorry about that. Next on the list, extraterrestrial radiation. This is equal to 1,366 watts per meter squared. It's the radiation just outside the Earth's atmosphere. Solar constant. The solar constant equals 1,366 watts per meter squared. It's the average of the extraterrestrial radiation. Solar radiation. This is all the radiation that comes from the sun. It includes gamma, visible light, X-rays, microwaves, radio waves. The atmosphere. For our purposes, that is the gas, the water vapor, and dust that surrounds the Earth. The inverse square law. The inverse square law states that the power of radiation decreases at the square of its distance. This is the formula. The energy that you will be receiving at distance is equal to the solar constant, 1,366, divided by the distance in astronomical units squared. And distance in astronomical units squared is actually the ratio of the distance an object is from a known distance, which is the distance the Earth is. Okay. Air mass. Air mass is the atmospheric mass that radiation must pass through in order to hit the Earth's surface. Its formula is the pressure at sea level, measured in millibars, over the local pressure measured in millibars, or inches of mercury, multiplied by the cosine of the zenith angle. So, as an example of this, I did Denver, Colorado today, right now. And to do this, you do the pressure at sea level, which is equal to 1,005 millibars, over the local pressure, which happens to be 1,013. You multiply that by the cosine of theta. Theta is the zenith angle of the sun, which is how high the sun is up in the sky. We're about to go through that actually right now. But right now, because it's 6 o'clock in the afternoon, the cosine of this theta is equal to 61.6. So you can see right away that cosine of 60 is about 0.5. So the cosine of 60 is about 0.5. 0.5 multiplied by 1013 is about 500. 1000 over 500 equals about 2. The actual answer is 2.08. And what that is that the actual mass of air that the radiation has to go through to hit the ground right now. Because the angle of the sun is low in the sky. Draw a little picture of this. When the sun is directly overhead, it goes straight through and hits the Earth's surface. And this is the air mass, this distance. When it's over here, and it goes all the way through there, this is the air mass. It goes through that distance. So if this is an air mass of 1, this is 60 degrees, this is going to be an air mass of 2. Cool. Inverse square law. To show the inverse square law, it's mostly useful for figuring out how much solar energy you have at different places in the universe. You can figure out, for example, what the wattage squared is on Mars. I did Uranus because I hadn't seen that example before, so here you go. This is the irradiance on Uranus. As you recall, the irradiance formula is the energy in watts per meter squared is equal to the solar constant, 1,366 watts per meter squared, over the distance in astronomical units squared. Uranus is 2.88 billion kilometers away, which makes it approximately 19.2 astronomical units. So 19.2, square that number, and you'll get 1366 watts per meter squared over 368.6 will give you 3.7 watts per meter squared. And that's on the surface of Uranus, or as opposed to the surface before there's an atmosphere. I don't even know if there's an atmosphere, but if there is, that's outside of it. So you can see the drop is drastic. We have 1,366 watts per meter squared. They have 3.4. So if you were to send a satellite into space, you'd need a substantial array to get any kind of power at that distance from the sun. And that'll hold true anywhere in the solar system. Right. Okay, more definitions. A pyranometer. A pyranometer is a light-sensing device that measures the total solar irradiance, including diffused irradiance. A pyrheliometer measures direct solar radiation. Does not measure any reflected, refracted, or just direct solar radiation. A reference cell is a PV cell that's been calibrated with a known output per irradiance. Couple of time definitions. Standard time is when the sun crosses a standard meridian. Solar noon differs from standard noon. Solar noon is when the sun is highest in the sky. It's exactly halfway between sunrise and sunset. Solar time is the sun crossing the local meridian. It references directly to solar south and differs significantly from standard. a couple more definitions for you. There's 3 angles we use to describe where the sun is in relationship to us. When we're looking at the sun from the earth, we reference it in the azimuth angle. In an azimuth angle, we find true south, and then the distance either west or east of that angle is our azimuth angle. In the afternoon, we'll have a much larger azimuth angle. At noon, we'll have, it will be 0. Okay, the next one is the zenith angle. The zenith angle the zenith itself is the point in the sky directly above where you are, 90 degrees from the theoretical flat surface of the earth. That's 90 degrees, that's the zenith. The zenith angle is the angle between that point and the sun, as it refers to this angle right here. The altitude angle is the complementary angle to that. That's the angle from the horizon to the angle of the sun, as viewed from the observer standpoint. That's the way we find the sun. We can describe it either in its azimuth and its altitude angle, or its azimuth and its zenith angle. And there you go. The next thing we're going to look at is a solar chart. You'll see a lot of these. I just want to teach you how to read one really quick. Make sure it's all on there. As you can see, it references the solar azimuth. These lines are the sun's path in any given month. At the very bottom, you're going to have winter solstice. At the very top, you're going to have summer solstice. In the middle, you'll have the months between. These smaller lines are labeled with times of day. This is 9 a.m., 10 a.m., the middle is always noon, 1 p.m., 7 p.m. On the left here, you're going to have a scale. These are altitude angles, like the ones we just talked about. So at any given time of day in any given month, you can find out what the sun's azimuth and what the sun's altitude angle will be. For example, at noon, and these will vary significantly by location. It'll say, if this chart was for a specific location, it would say, solar azimuth east-west for the location, Denver, Colorado. For the location, Los Angeles, California. For the location, Nazareth, wherever it's done. So, for example, at solar noon, and these are solar times, they are not standard times. For example, at solar noon on December 21st, the solar altitude angle will be 30 degrees, and the azimuth angle will be 0. It can be confusing sometimes because when we're talking about solar azimuth angles, half the time they'll reference true south as 0, and half the time they'll reference true south as 180 degrees. Don't get confused. Another example is, in July at 9 a.m., the sun will be at 45 degrees, altitude angle. It's the way you can, these sun charts are what you'll use in your sun pathfinder later to determine shading. They're also, there's a lot of uses, and you'll see it once more. And one more time, I couldn't do a chapter on the sun without actually bringing out a bright orange model, so I brought out a bright orange model just to explain a couple of different terms really quick. So this is my Earth. This is the North Pole. That's the angle of the Earth. This band is the equator, Northern Hemisphere, Southern Hemisphere. The two terms I'm going to describe to you are the equatorial plane. The equatorial plane is the plane, it's a fictitious line of reference that goes through the equator, and it extends out into space indefinitely. So here you go. I made a little model. If I can line it up so it doesn't look stupid. That is the equatorial plane of this globe. It goes right through the equator and it extends out into space. The elliptical plane is the plane that is directly from the sun through the center of the earth. So if you were being the sun, this would be your elliptical plane. It would look directly at you. As the equatorial plane crosses through this way, and the elliptical plane crosses through the center of the sun and the center of the earth as it travels around, the difference between this plane and this plane is called the solar declination. Screw it up. And the real definition of the winter solstice is the time with the greatest solar declination to the south. And the summer solstice, the greatest solar declination to the north. And during the equinox, there is zero. The total solar declination is zero. And there you go. Okay, there's one last thing I wanted to go over in this video, and that's tilt angles and latitude. Latitude is, of course, the distance from the equator. In the northern hemisphere, we are north of the equator on the planet. The latitude angle is the same angle as the best angle to mount your PV array. If you live at 22 degrees north latitude, chances are your PV array will be tilted at 22 degrees towards the south. If you wanted to increase production for the winter time, you would tilt it a little bit more, which makes sense. The sun is a little bit lower in the sky in the wintertime. You tilt your array a little bit higher, you'll get a greater angle of incidence in the winter. In the summer, exactly opposite. If you wanted to maximize array production in the summertime, you would lay it a little bit flatter. You would have a lower array tilt angle, and you would have a better angle of incidence in the summertime. There's a way to get around this angle of incidence problem, is to get a single or dual axis tracker. The single axis tracker generally tracks east-west and will follow the sun either with a solar eye or it can be put on a timer. It can increase your production about 25%. A dual axis tracker will track north-south and also will track east-west, and it can increase your production to about 30%. Generally, in residential settings, you won't see single or dual axis trackers. They're not, they're maintenance heavy and they're expensive. So, this angle of incidence is an important term to understand. It's the angle at which the sun is to the PV panel. Obviously, the best angle is 90 degrees. You want the sun shining directly onto your PV panel. However, because the sun appears to be higher in the summer and lower in the winter, you have to choose a median. You have to choose, and at any given time, using sun measuring equipment, you can see the angle of incidence on your PV array. The angle of incidence won't. You can have, 10, 15% plus or minus on your angle of incidence based on your particular installation, and you can still pull about 95% of the same power. It's in theory, it's important to go with the ideal. In practicality, it's important to go with what you can actually do. And the solar window. The solar window is the altitude angles and the azimuth angles from summer solstice to winter solstice. It encompasses, on the sun chart, it encompasses this area. It's the area that in the sky where you'll actually see the sun. Areas below that line, you probably will never see the sun. Areas above that line, you know, the sun won't be there either. And it's important to aim your array towards your solar window. And that's all about the sun for PV Chapter 3. Thank you guys so much. The next chapter we're going to go into is home energy auditing, how to determine a home's energy needs, how to determine the size of PV array should need. We're going to go over the different kinds of systems, battery-based systems, the standalone battery-based system. We're going to deal with the grid-tied inverter-based system. It's going to be good times, so come back for my next video. I hope this video moved a lot better. I hope it was a lot clearer. I hope you can hear my voice through the whole thing. Let me know, and thank you very much.